Hello everyone, welcome back to our latest lecture session, right? So we have been discussing, I believe, acidity in great detail in the last class, and prior to that we discussed alkalinity. So obviously, we are going to look at the applications, right? As in how you are going to end up using alkalinity mostly. We'll have maybe a minor application with respect to acidity. So primarily today's session we are going to try to understand how to apply acidity with respect to various scenarios, right? So let's get right down to it. So initially, what have we been doing until now? In our acid and base systems, what kind of problems have we been looking at? Primarily recipe problems, right? Recipe problems as in, what did we look at? Let's say I considered different examples, or all the examples that we looked at so far have been, I know what it is I am adding initially, as in let's say I know the amount of acid I am adding initially or amount of base I am adding initially, and I am using VMINTEQ or the component balance approach, solving it out manually to be able to calculate the relevant species at equilibrium, right? So what have we been up to? So let's look at a minor example. Let's say, I know H2CO3 not present initially, or Na2CO3 not present initially, right? So from that we calculated either H total or CO3 total and Na total, and either we use VMINTEQ, right, or by hand or component balance, right? And then what did we solve for? Primarily we are trying to find out what will be the equilibrium concentrations, right? So this is what we discussed in general. So this will work fine whenever you are looking at engineered systems, right? Let's say I am conducting an experiment. I know what it is that I am putting in initially. I want to know the pH that I would expect, or the alkalinity that I would expect, or acidity I would expect, and so on, right? So that will help with your engineered systems. But let's say if I am looking at let's say natural systems or real world systems, or the different kinds of problems you would routinely face. What are they, for example? Let's say I have water quality analysis, right? What parameters will they have? They will have, let's say, pH, alkalinity expressed as CaCO3 or equivalents, but rarely equivalents. People end up in India anyway using the units of as CaCO3, right? And then we need to end up estimating, let's say, or we might need to end up estimating what are the relevant concentrations of the species. For example, let's say, if you look at a water quality report, let's say, what would you have? Let's say you will certainly have pH, and other than the physical parameters, let's say you will also have alkalinity, and let's say you will also have phosphate, but it's not phosphate, right? It's total phosphate that people end up measuring, right? So you have, let's say, what now? pH, alkalinity, and total phosphate. But let's say I want to be able to understand what are the concentrations of the relevant species at equilibrium, right? Or what are the different species present and in what concentrations. How do I do that? Because here, let's say, we are not saying we are inputting so and so solutions, and then I want to calculate estimate more or less, right? What the equilibrium concentrations are going to be. Here, let's say I have a solution, and the pH, alkalinity, and the relevant total component concentrations of various components are given. For example, in this case I mentioned total phosphate, right? How do I estimate the concentrations of the relevant species? So that's what we are going to look at in greater detail. So this we are going to look at as water quality problems. Until now we looked at recipe problems. I know what it is my recipe is, as in the recipe solutions. One example is what we looked at when we added H2CO3 or Na2CO3 initially, and I wanted to know, okay, what are the concentrations of H2CO3, HCO3 minus, CO3 2 minus, pH, etc. at equilibrium. This is what we calculated until now, right? Yes, but in general, what do we face? We face scenarios, let's say, where we have, let's say, pH, we have alkalinity given, right? And then we also have, let's say, for this example, X total, but let's say one example can be total phosphate present, right? And then let's say we are trying to estimate, let's say, what are the various species at equilibrium, right? So So obviously we are going to look at alkalinity in this particular case, and then we are going to move on to more complex systems, but one step at a time, I guess. So this is the case again. So again, as we know, I guess, right, what is it about, what is our approach about? It's about more or less being able to calculate the total components, right? But here if you look at this system, we have pH and alkalinity, but we don't have the relevant components there, or total components, pardon me. But we obviously have one other total component. We have phosphate total here, let's say, or X total in this particular generic example, right? So how do I go about estimating the equilibrium concentrations, right? So what am I missing here? Obviously, if you understand what it is that we have been up to, we were earlier trying to transform the recipe concentrations and express them in terms of the total component. So here we do not have that, we have pH and alkalinity. So what can I get from them, or what information can I glean from them, right? So obviously if you are looking at component balance, we obviously need to try to find out the H total and CO3 total. Why? Alkalinity in general, we look at it in terms of the carbonate system, and thus we are going to look at CO3 total, right? So first we will try the manual approach, as in how to express, or how to, let's say, calculate CO3 total given pH and alkalinity. It's relatively simple, obviously. And then we will also see how to use VMINTEQ, which obviously, cuts down on the time required, right? So first aspect is that, it's a closed system, right, when you have no exposure of the relevant solution to the atmosphere, right, no gaseous phase present. So here we are going to consider a case where we have pH, alkalinity and X total, and what am I trying to calculate? I am trying to calculate the equilibrium species, the concentration, I guess, the concentration of various equilibrium species. So how do I go about that? First manually, I guess, right. So alkalinity, what's our equation with respect to alkalinity now? We know that it's going to be equal to, what is it here please, OH minus, right, and the other bases are HCO3 minus plus 2CO3 2 minus H plus, right. And how can we simplify this further? Let's say we are trying to express everything in terms of variables such that we can end up with H total and CO3 total. So obviously I need them in terms of H plus and CO3 total, right. So let's see how I can transform that. So alkalinity is given, right, alkalinity is given in our particular case, and pH is given, so I want to express in terms of H plus. So OH minus we know is Kw by H plus, and where does this come from? Because the water can dissociate into H plus and OH minus, and the water dissociation constant is going to be equal to H plus into OH minus, right. Again, just to refresh our memories, fundamentally what is it? Kw equal to activity of H plus, right, and activity of OH minus by activity of water, but activity of water, right, in this dilute systems is going to be equal to 1, and we are approximating the activities by concentration. So right, so that's where we end up with, or that's how we end up with this particular equation, and minus H plus, right. And how can I express HCO3 minus and 2CO3 2 minus in terms of CO3 total now? And obviously as we know, right, we looked at the ionization fractions. So alpha naught is nothing but H2CO3 concentration by CO3 total, and similarly the first, second and third ionization fractions in this case are, what are they? HCO3 minus by CO3 total and CO3 2 minus by CO3 total, right. Again, just to refresh your memories, we talked about this, I guess quite some sessions ago, this as in the ionization fractions. So what do these ionization fractions give you an idea about? Obviously as we just tried to jot them down, we understand that each ionization fraction will give you an idea about the relevant protonated or deprotonated form in terms of the total acid concentration, right. So for example, the relevant species for us are HCO3 minus and CO3 2 minus. So how can we express them as? Alpha 1 is equal to HCO3 minus by CO3 total, and alpha 2 is CO3 2 minus by CO3 total. And what's CO3 total now? In general, CO3 total, if you write it down in this case, should be equal to HCO3 minus plus H2CO3 plus CO3 2 minus, right, total acid concentrations in this case anyway. Yes. So anyway, let's try to use that here. So that's then going to be equal to, how do I transform these two variables? Going to be equal to alpha 1 plus 2 times of alpha, this is alpha 2, pardon me, right, alpha 2 into, and from this set of equations, you know, into CO3 total, right. So, what do we see here? Given that you have the alkalinity and given that you have pH or H plus, you can end up calculating the CO3 total, right. You know that alpha naught, pardon me, alpha 1 and 2 alpha 2 are, you know, constants for a given pH. So, you can calculate them, they are more or less constants given that you know the pH and the relevant system, which in this case is carbonate system. So, here with the pH and alkalinity, right, we end up calculating the CO3 total, and once we have that we can also calculate H total, right. So, once we have H total, CO3 total and X total, we have the relevant total components, right. So, once we have this, obviously what can we solve for? We can solve for the species or the concentration of species. More or less species means what are they? The compounds present at equilibrium, right. So, we are able to solve that. This is manually though, right. But again, solving that manually is obviously going to take some time, right. So, let us look at one particular example or such where we are going to use VMINTEQ, but you know we should always be able to understand the basics behind it, and we will see why later on when we look at a minor example, I guess, right. So, here we are going to start looking at VMINTEQ, right, and let us take a particular case, let us say when pH, let us say is 7, right, and alkalinity let us say is 30 milligram per liter expressed as CaCO3, right, and let us say my X total, in this case let us say PO4 3 minus total is equal to let us say 0.01 molar or molar units, which we are approximating is equal to molar units in VMINTEQ. If required we will change this later, but for example let us take this down. So, you can either use the units of alkalinity as CaCO3, we will see how, right, or we can transform that, and how do we transform that? Is equal to 30 milligrams of CaCO3. I try to express them in terms of the relevant compound so that it is easier to understand per liter of water, right. If I want to transform that into equivalents per liter, so I am going to divide that by, I know that it is going to be 50 milligrams of CaCO3 per 1 equivalent, I guess, right. So, where did we get this from? Calcium carbonate, the molecular weight is 100, I guess, right. 40 plus 12 plus 3 times 16 is, I guess, 48, right. 48 plus 12 60, yes, 60 plus 40, that is equal to 100. But we know that you know it is Ca2 plus and CO3 2 minus, if they can dissociate into that, right. So, more or less we end up with 2 equivalents, right, per 100 grams of CaCO3, right. So, there is more or less 1 equivalent per 50 grams of CaCO3, right. Anyway, that is the what we say background here. So, that we end up with 30 into 10 power minus 3 by 50 equivalents per liter. So, that is equal to 3 by 5 is 0.6 or 6 into 10 power minus 4 equivalents per liter, right. So, that is something that we just have as a background. So, let us now switch out to VMINTEQ, right, and understand the system. So, again what do we need to do? Let us switch back. What do we need to do here? So, we have the pH, we have the alkalinity, right. VMINTEQ can't calculate whatever it is that you want randomly. So, what do we need to do initially? We obviously need to calculate what is the CO3 total, right. So, how do we do that? Let us look at that. So, let us switch. So, here what was our pH? I think we said pH was 7. So, the pH I am going to fix it at 7, that is the value that we already have here, and we know we have alkalinity. So, let us go to specifying alkalinity. As you see here, you have different units as milligram per liter of HCO3 minus, CO3 2 minus, CaCO3 are milli equivalents per liter. So, I did not have transform the units from milligram per liter of CaCO3 to milli equivalents, but anyway for understanding we did that. So, that is fine. So, we transform that into equivalents per liter, right. So, and that we end up with 6 into 10 power minus 4, which is 0.6 milliequivalents, right. Hopefully I am right. And normal, we will go through this particular case later. Again, pH 4.5 is because you titrated to pH 4.5, and normal definition here you can understand the difference if you want to. So, I plug that in. So, and now I run VMINTEQ, the number of components is equal to the number of fixed species. Okay. Obviously, I see that there is an issue there because L as expected, right. So, let us go back to the VMINTEQ menu and view edit list. So, let us say something else needs to be given here, right. So, I need to give back to main menu, let us say, and also let us say I am going to have Na plus. And act guess, I will try to see if we can let the system guess. Okay, again visual MINTEQ species including the input file as fixed, possible, finite, or was not, or excluded was not in the thermodynamic database. So, I think let me understand the system here. Okay. So, CO3 2 minus, Na plus, back to main menu. Let me add H plus. I think that is the reason why we are ending up with an error. Let us see where is H plus here. Okay. Add to the list, view edit list. Let me try if this should hopefully solve this issue, or I think I still need to add the Cl minus. We will come back to that. Anyway, one good way is to learn by what do we say, what we are up to. So, anyway, looks like because I did not have H plus or deleted H plus by error, we end up with an issue, right. So, where do we have this particular, let us look at species distribution once. So, pH 7 you would assume that, or you would expect that everything would be present as HCO3 minus. So, that is what most of it as of CO3 total is present as HCO3, and that is what you see here, 81 or 82% is present as what do we say, HCO3 minus, and H2CO3 is 18% of the CO3 total, right. That is what you would expect when the pH is 7. Back to main output menu, and now here let us say where can I get the CO3 total here, please. So, I can go back to species distribution, not really, or now I can sum up the CO3 total from here, right. CO3 total will be equal to CO3 2 minus, H2CO3 and HCO3 minus. So, I can sum up these three values, and then I will end up calculating my CO3 total, right. So, that is what I can see from here, and view species distribution, pardon me, display saturation indices. This is when we have to look at, let us say, saturation or precipitation and dissolution, which we do not go into right now. So, now from this particular graph I can end up calculating not graph, pardon me, from this particular set of values I can end up calculating the CO3 total, right. CO3 2 minus, H2CO3 and HCO3 minus, the sum of them will give me my CO3 total. So, I inputted pH at 7, alkalinity at 0.6 equivalents per liter, and I can calculate my CO3 total, right. For sake of ease, let me just take it as this is what do we say, 10 power, okay, 6 point, HCO3 minus is, let us say this is 6, I will say it is 7.2 into 10 power minus 4, let us say bigger. 7.2 into 10 power minus 4. Let me take that and then try to plug in the relevant values. It is not equal, you can use the Excel and get the relevant values, right. So, again what are we up to here? I am trying to calculate the component balance in terms of CO3 total, and because Excel, or pardon me, VMINTEQ can't do that by itself, we plugged in pH, and in parameters we plugged in alkalinity in the terms of equivalent per liter units, and then looking at the relevant species I can calculate the CO3 total, right. So, let us come back to this. Obviously, I can print it to Excel and get the relevant what do we say, species concentration. So, if I go back to main menu, view edit list. So, earlier I made the error of having inadvertently deleted H plus, that is why we looked at an error, right. And where are the output files? Okay. Here are the output files. So, you can look at the relevant concentrations here and calculate that. So, now I am going to change it such that, how do I change it? That I want to also put in phosphate total, right. So, let us see how I can go with that. Specify alkalinity, let us say now I am going to say no, there is no alkalinity specified in the solution, right? View edit list, and now CO3 total is going to be relatively what was it, I think 7.4, right? 7.2 into 10 power minus 4, right? So let's plug that in here. CO3 total, back to main menu, and CO3 total, and the key, let's say I will use millimolal. So if I use millimolal, I just need to plug in 0.72 millimolal, right? And so here I'm going to plug in 0.72 and add that to the list. And what else do I have here, please? I also have phosphate, and what was that? That we said was 0.01 molal. That's a bit of a high concentration, so let's look at that later. So now pH is not fixed anymore. Let's say calculated from mass balance, let's say. Let's see if that will work out. Not really. I'll leave the pH at 7 because I know it's at 7. And PO4 3 minus, PO4 3 minus, and I said I'm going to use it at a molar concentration of 0.01, right? Or to make it relatively similar, I'm going to change it such that it's 0.001 or 1 millimolal, right? Otherwise it might be way too high. So here I have 0.002 H and so on. Back to main menu, and pH is fixed at 7. So now I can calculate the relevant concentrations of the relevant species, which are H2PO4, H3PO4, HPO4 2 minus, which I was unable to do earlier. So I look at the relevant species distribution, right? So CO3 2 minus, it's present obviously at 82% in HCO3 minus, and PO4 3 minus is present as HPO4 2 minus and H2PO4 minus, right? So let's just summarize what we were up to, right? Back to input menu. So keep in mind that we changed this particular value to make it similar. So again, manually we saw how to do that. So again, let's summarize pH and alkalinity. We plugged them in initially, right? And then we ended up from this particular information calculating CO3 total, and we already have PO4 total, right? And using this information, right, and also fixing the pH at the given value, which was pH 7, I then ended up calculating all the species concentration, and what were they? H3PO4, right? H2PO4 minus, HPO4 2 minus, and PO4 3 minus, and so on, right? So this is what we can do. So obviously we need to transform it such that we get the first components that we need to look at and then go through, right? So this we are done with this for now. So let's move on to an open system, right? And where is that? So open system, I guess. And what is this about? So when this case is when you have your particular system here, but it's open to the atmosphere or the gaseous phase, let's say, right? And here you can have, what do we say, as we know, transfer of carbon dioxide or CO3 total between the gaseous and the aqueous phase. So for this we looked at the relevant what do we say, transformations and such earlier. Obviously we are not going to go through that, but we are going to look at relevant applications, I guess, right? So let's see. So obviously here, instead of CO3 total, right, which we did in the closed systems, obviously we are going to try to express our terms, our alkalinity in terms of partial pressure of carbon dioxide. So let's see how we can do that. I think we might have looked at a minor transformation earlier. So we know that alkalinity is equal to alpha 1 plus alpha 2, alpha 1 plus 2 alpha 2, because it's 2 times CO3 2 minus into CO3 total plus Kw by H plus minus H plus, right? And what is this equation though? This equation is when we have alkalinity initially, I guess. This is the alkalinity equation for initial cases. But let's say now you have carbon dioxide that's in equilibrium with your particular system. So well, what do we need to do now, I guess? So that's the case. So here we have alkalinity here, and we have, let's say, partial pressure of carbon dioxide. So how do I go about this particular case now, right? So again, the key aspect that we need to consider here is that from what we discussed a couple of sessions ago, we know that alkalinity does not change when you introduce carbon dioxide into the system or remove carbon dioxide from the system, right? So how was that, or why did we come up with that? Alkalinity was equal to what now? OH minus, and the other bases are HCO3 minus plus 2CO3 2 minus minus H plus, right? And we saw that when we bubbled carbon dioxide, it can go to H2CO3 or H plus and HCO3 minus, or it can directly, let us say, also go to 2H plus and CO3 2 minus. So if we plug in the relevant variables, we see that 2CO3 2 minus and minus H plus, or HCO3 minus and minus H plus, so they cancel each other out, right? So again, if you remember what we discussed, introducing or removing carbon dioxide from your particular solution will not affect alkalinity. Obviously the pH is going to change, right? But it's not going to change the alkalinity. So this is the key here, as in the alkalinity before and after equilibrium with your gaseous phase is going to be the same, right? So let's use that. So let's say if I assume that if equilibrium with CO2 is achieved, right, the alkalinity is still going to be the same, right? Alkalinity is same. But obviously I want to transform CO3 total into what do we say, partial pressure of CO2. So CO3 total, I want to express it in terms of partial pressure of CO2, right? So in this case we looked at one particular aspect earlier, so I think we talked about H2CO3, right, and that it was equal to what now, in terms of CO3 total it was alpha naught into CO3 total, right? And then we talked about the Henry's constant Kh, right, and then we tried to solve for it. Henry's constant, what will that give me an idea about? Partial pressure of CO2 by concentration of H2CO3 in the aqueous phase, right. So that is going to be equal to partial pressure of CO2 by alpha naught into CO3 total, right. This is something I believe we looked at previously. So Kh is going to be equal to PCO2 by alpha naught into CO3 total, right. But depending on the units, let us say if it is K dash H, wherein the units are moles per atmospheres, this is then going to be equal to alpha naught into CO3 total by partial pressure of CO2. Again, the key is that the units are going to be or can be different, right. So you need to look at the units whenever you are looking at the Henry's constant, right. Again, to refresh our memory, we are just trying to use Henry's constant to get a relationship between partial pressure of CO2 and CO3 total, right. And what does Henry's constant give us an idea about? It gives us an idea about the concentration in the gaseous phase of a compound to the concentration of the compound in the aqueous phase. In this case, we are talking about CO2. So we say that Henry's constant, depending on the units, is either going to be the partial pressure of CO2 in the gaseous phase to the concentration of H2CO3 in the aqueous phase, or if the units of the Henry's constants are vice versa, as in or the inverse, let us say, as in if it is moles per liter per atmospheres, it is going to be Henry's constant, or K dash H is going to be equal to H2CO3 concentration by partial pressure of CO2, right. So I believe we used this particular term earlier, so I am going to continue using this. So how can I express alkalinity here? So alkalinity is now going to be equal to alpha 1 plus 2 alpha 2 into, right, where do I have that? So I have CO3 total. So CO3 total in this case is equal to K dash H into partial pressure of CO2 into alpha naught. So that is going to be equal to CO3 total is equal to K dash H into partial pressure of CO2 by naught into alpha naught divided by alpha naught, obviously, right, partial pressure of CO2 by alpha naught plus Kw by H plus minus concentration of H plus, right. So in this way we can simplify the particular system further and you can solve for the relevant aspects, right. So again, we just try to, this is the manual approach, so we are obviously going to look at how to get that done if it's, what do we say, in the, if you are trying to use VMINTEQ, right? So again, what have we done here? We just try to express CO3 total in terms of partial pressure of CO2. And why is that so? Because this is an open system, as in the, what do you say, your solution is open to the gaseous phase, and there can be a transfer of CO2 or CO3 total, obviously, right, from the gaseous to the liquid or liquid to the gaseous. So that's the reason we looked at alkalinity. And again, why alkalinity? Because alkalinity does not change when there is any exchange of CO2 between the gaseous and aqueous phases, right? So let's try to use VMINTEQ and try to look at a particular scenario, pardon me. So let's go back to VMINTEQ and see how we can go through with that. So now let's edit the list from what we were up to earlier, right? So I'm going to view edit the list, I'm going to delete this, I'm going to delete this for now, and back to main menu. And so I'm going to say there is pH and alkalinity, right? Enter pH and alkalinity, specify alkalinity, and there is alkalinity now, and let's say it's present as 30, in my case 30 milligram per liter as CaCO3, which we looked at earlier, right? So okay, and pH is going to be fixed at 7, let's say, for my example, right? And view edit list, okay, so it already obviously calculated the case for that. Back to main menu, and then run MINTEQ, right, pH 7 and so on, yes, and we can get the CO3 total from here, H2CO3 and such. So obviously from here what can I calculate? I can calculate, so by plug in pH and what is it please, alkalinity, I can then end up calculating H total and CO3 total, right, from VMINTEQ again. And now what I am going to do, I am going to enter CO3 total, H total, and now give a partial pressure of CO2, right. Let us give a random value there, and then we can come up with our particular case, I guess. So instead of calculating the aspects, I am going to go ahead and get that done with some random values. Obviously you can calculate H total and CO3 total here. So back to input menu and view edit list. So you hopefully this should even might turn out to be the same. And what next here? We are trying to input CO3 total, H total and PCO2. So strictly speaking, I need to calculate that from the previous particular VMINTEQ output, but I am going to use random values and see how we can go through, right. So H total, CO3 total and PCO2, let us go back to that. So here now parameters, I am going to say there is no more alkalinity now, right, because I am going to input CO3 total, right. But gases, I know that I need to specify gases. How do I do that? And pressure, so I am going to change it, let us say that it is going to be 2 times, let us say, than what I would expect in the atmosphere. What is this tab here? So it says specify the fixed CO2 partial pressure, and atmospheric CO2 pressure is given, which I am going to say is constant, but in my case I am going to say the partial pressure is 2 times what I would expect in the atmosphere. So that is what we see here. Enter the partial pressure of CO2 as a multiple of X above. So I am going to say it is going to be equal to twice of what I would expect, or let us say go with thrice of what I would expect in my atmosphere. This is a hypothetical example I am looking at. So I am going to click add and back to main menu. So I need to also give the CO3 total, right, CO3 total, where is that, CO3 total, and let us say I am randomly going with 0.001, add to list, right, view edit list, yes, back to main menu and run MINTEQ. Okay, so because the charge is not balanced, so it is going to take Cl minus at particular concentration, and now I can end up with my relevant aspects after PCO2 is taken into case. So as you see, PCO2 is now present at this particular partial pressure at equilibrium, right. So with that I am going to end today's session. Again, the crux of the issue is we transformed using pH and alkalinity, we ended up calculating CO3 total and then used the relevant aspects in the closed system. But in the open system, what were we up to? We calculated pH and CO3 total, H total and CO3 total from pH and alkalinity, and then use that to have the partial pressure of CO2. Why is that? Because it is an open system, and then calculate the relevant species. Obviously in this example I did not plug in PO4 total, so I could have plugged in PO4 total and so on and so forth. But here one case is that, you know, if I remove the pH, because let us say pH is not going to be constant when partial pressure is, let us say, changed, calculate from mass and charge balance. So I run that. So obviously as I see here, this is something I should have done earlier. The pH is not going to stay the same, which was the initial case earlier, but the pH is going to fall. Why is it going to fall? Because I increased the or introduced a new variable in terms of partial pressure of CO2. As in, let me just clarify that. So earlier the pH was 7, right, and there is a given alkalinity, and then I end up calculating, you know, the relevant CO3 total and H total, which I assume random values, I guess, right, which maybe given time we will do that later. And then I plugged in the value for partial pressure of CO2 and then ran VMINTEQ, and what did I get? I got a pH of around 5.3, right. But if I calculate CO3 total, or not CO3 total, pardon me, the alkalinity should still be the same, right. So that is what we see here, and with that I will end today's session, and thank you.